Three-phase inverters. The three-phase inverters are normally used for high power applications. Three single-phase half or full bridge inverters can be connected in parallel as shown in this figure to form the configuration of the three-phase inverter. The gating signals of single-phase inverters should be advanced or delayed by 120 degrees with respect to each other in order to obtain three-phase balanced voltage. The transformer primary windings must be isolated from each other, while the secondary windings may be connected in Y or delta. The transformer secondary is normally connected in Y to eliminate triplean harmonics, that is n equal to 3, 6, 9 and so on, which appears on the output voltages. And the circuit arrangement is as shown in this figure. This arrangement requires 3 single-phase transformers, 12 transistors and 12 diodes. If the output voltage of a single-phase inverters are not perfectly balanced in magnitude and phases, the three-phase output voltages will be unbalanced. This is the configuration of 6 transistors and 6 diodes to obtain three-phase output voltage. Two types of control signals can be applied to the transistor. The first one is 180 degrees conduction. Second one is a 120 degrees conduction. We'll see the first one, 180 degrees conduction mode. Each transistor conducts for 180 degrees. 3 transistors remains on at any instant of the time. When Q1 is switched on, the terminal A is connected to a positive terminal of the DC input voltage. When Q4 is turned on, the terminal A is brought to the negative terminal of the DC source. There are 6 modes of operation in each cycle and the duration of each mode is 60 degrees. The transistors are numbered in sequence of gating the transistors, that is 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, 5, 6, 1, 6, 1, 2. The gating signals are shifted from each other by 60 degrees to obtain three-phase balance fundamental voltages. Now let us see the gating signal. The gating signal G1 is going to remain 180 degrees on and then goes to 0 for 180 degrees. Then again it starts next 180 degrees. Now the gating signal of G2 is going to start at 60 degrees and remains on conduction for 180 degrees, then stops to next 180 degrees, then starts conducting after this. Gating signal 3 is going to start at 120 degrees and conducts for 180 degrees, be off for 180 degrees next, then starts conduction. The gating signal for fourth transistor is going to start at 180 and conducts 180 degrees, then stops conduction for next 180 degrees. The G5 gating signal is going to start at 180 plus 60 and conducts for next 180 degrees and then stops conduction for next 180 degrees. Conduct in from 0 to 60 degrees before also. Now the gating signal 6 is going to start after 60 degrees of gating signal of 5, then conducts for 180 degrees, then stops conduction. Then it's going to start conduction in this period. These are the 6 gating signals for the transistor to be triggered. Now when Q1 is on, the A is connected to upper source Vs by 2, and when Q4 is on, A is connected to lower Vs. So it's going to give a positive voltage, it's going to give a negative voltage of A. Now similarly, when Q3 is on, B is connected to Vs by 2, a positive supply, and when Q6 is on, B is connected to minus Vs by 2, so negative will be given for phase B. When Q5 is on, C is connected to positive, so positive voltage will be given, and when Q2 is on, C is connected to minus Vs by 2, then negative voltage will be given for the phase C. VAB will be positive when Q1, Q6 are turned on. Let us see, in 60 degrees, G1 and G6 are on, so VAB will be present and the value will be Vs. And 62, 120 also G6 and G1 are present, so this is going to be Vs. Now to get minus VAB, need Q3 and Q4 should be turned on. G3 and G4 are on from here to here. So from here to here we'll be getting minus VAB. Then again at 2 pi again we are going to get a positive voltage. Now VBC will be positive when Q3 and Q2 are turned on, and minus VBC we are going to get when Q5, Q6 are turned on. G3 and G2 is going to be present between these two areas. So from here to here we'll be getting VBC equals to VS. Q5 and Q6 both are present in this area. So from here to here again, here it's going to start. This is VBC. VCA will be positive when Q5 and Q4 are turned on, and VCA will be negative when Q2, Q1 are turned on. The G4 and Q5 both are present from here to here. This is VAB, VBC, VCA. These are the waveforms for 180 degrees conduction. The load may be connected in Y or delta as shown. For delta connected load, the phase currents can be obtained directly from the line to line voltages. Once the phase currents are known, the line currents can be determined. For Y connected load, the line to neutral voltages must be determined to find the line or phase currents. There are three modes of operation in a half cycle, and equivalent circuits for Y connected load are shown during mode 1 for 0 less than or equal to omega t less than or equal to pi by 3 from the circuit. R equivalent equals to R plus R by 2, which equals to 3 R by 2, and the current I1 is given by Vs by R equivalent, that equals to 2 Vs by 3 R. Then VAN equals to VCN, that equals to I1 R divided by 2, which equals to Vs by 3, and VBN equals to minus I1 R, that equals to 2 Vs by 3 R multiplied by R, that equals to 2 Vs by 3. From the circuit during mode 2, that is for pi by 3 less than or equal to omega t less than or equal to 2 pi by 3. R equivalent is equals to 3R by 2, and I1 equals to 2 Vs by 3R. Here VAN equals to I2, sorry, this is I2 for the second circuit, R, that equals to 2 Vs by 3R, R gets cancelled 3, and VBN equals to VCN, that equals to minus I2 R by 2, that equals to minus Vs by 3. Now during mode 3, that is 2 pi by 3 less than or equal to omega t less than or equal to 3 pi by 3, which is nothing but pi. Here also R equivalent equals to 3R by 2 from the circuit. I3 equals to 2 Vs by 3R. VAN equals to VBN, that equals to I3 R by 2, that equals to Vs by 3. Now VCN equals to minus R3R, that equals to minus 2 Vs by 3. These are the three modes within 180 degrees. If you extend for another 180 degrees, then you are going to get mode 4 for 3 pi by 3 less than or equal to omega t less than or equal to 4 pi by 3, where VAN, VCN equals to minus Vs by 3, and VBN equals to 2 Vs by 3. Mode 5 between 4 pi by 3 omega t 5 pi by 3. VAN equals to minus 2 Vs by 3. VBN equals to VCN equals to Vs by 3. And for mode 6, between 5 pi by 3 less than or equal to omega t less than or equal to 2 pi. 6 pi by 3 is nothing but 2 pi. Here VAN equals to VBN equals to minus Vs by 3, and VCN equals to 2 Vs by 3. Let us try to draw this information in a waveform. Now, the line to neutral voltages are shown. The instantaneous line to line voltages VAB can be expressed in Fourier series that VAB equals to sigma n equals to 1 3 5 to infinity 4 Vs divided by n pi cos n pi by 6 sine n of omega t plus pi by 6. Let it be equation A. VBC and VCA can be found by phase shifting VAB by 120 degrees and 240 degrees. So VBC equals to sigma n equals to 1 3 5 infinity 4 Vs by n pi cos n pi by 6 sine n of omega t minus pi by 2. That is B. And VCA equals to sigma n equals to 1 3 5 to infinity 4 Vs by n pi cos n pi by 6 sine n of omega t minus 7 pi by 6. That is BC. Now we can notice that from the above equations, the triplet harmonic, that is n equal to 3, 9, 15 would be 0 in the line to line voltages. The line to line RMS voltage can be VL equals to 2 by 2 pi integral 0 to 2 pi by 3 Vs square d omega t, another square root, which equals to root 2 by 3 Vs, which equals to 0.8165 Vs. Let this be equation D. From equation A, RMS nth component of line voltage, that is VLN, equals to 4 Vs by root 2 n pi cos n pi by 6. Let it be E. For n equal to 1, VL1 equals to 4 Vs cos 30 degrees divided by root 2 pi, which equals to 0.7797 Vs. Let it be F. Now the RMS value of line to neutral voltage can be found from the line voltage, that is Vp equals to VL by root 3, that equals to root 2 Vs by 3, that equals to 0.4714 Vs. Let it be G. With the resistive load, the diode across the transistors have no functions. If the load is inductive, the current in each arm of the inverter would be delayed to its voltage as shown in the figure. When transistor Q4 is off, the only path for the negative line current IA is through D1. Hence, the load terminal A is connected to the DC source through D1 until the load current reverses its polarity at t equals to T1 as shown in the diagram. During the period for 0 to T1, the transistor Q1 will not conduct. Similarly, the transistor Q4 will only start to conduct at t equals to T2. The transistor must be continuously gated since the conduction time of the transistor and the diodes depends on the load power factor. For a Y-connected load, the phase voltage is VAN equals to VAB divided by root 3 with a delay of 30 degrees. Now from equation A, the line current IA for the RL load is given by sigma n equals to 135 to infinity 4 Vs divided by root 3 times of n pi square root of r square plus n omega L square cos n pi by 6 of sine n omega t minus theta n. Let it be equation H, where theta n equals to tan inverse of n omega L by R. So this is regarding 180 degrees conduction mode of a three-phase inverter. If this video is useful, please like, share and subscribe.